Let's take a look at exercise number 60. Part A asks us to prove that the equation natural log of x equals 3 minus 2x has at least one real solution. And then part B asks us to use a calculator to find an interval of length 0.01 that contains a solution. So let's look at the first part first, as is usually a good idea. Now, we're asked to prove that this equation has at least one real solution, and that should kind of, raise some concern. This sounds like we're going to have trouble finding what that solution is. And indeed, when we have this combination of a natural log with a polynomial function, it will be difficult or probably impossible to analytically solve this equation. So we cannot, through just pencil and paper means, find an exact representation of what x is, if there is any x that does exist. So it's a useful question to even ask, is there a solution to this equation? So we're going to want to use the intermediate value theorem here. And that will involve comparing a function to some fixed value. It's usually easiest to compare these things to 0, because then you can just look at positives and negatives and work out from there. So we could rearrange that equation as 0 equals 3 minus 2x minus the natural log of x. We could have instead just added the 2x to the other side and had natural log of x plus 2x equals 3, and then 3 would have been the target number we were looking at. But this is a general technique that works even if you don't have constants, so I'll go ahead and do it this way. But you could just take a simpler function compared to 3 if you wish. It's very useful to give the function a name. We can call it basically anything we want, but of course f is traditional. So let's let f of x equal that right-hand side, 3 minus 2x minus the natural log of x. Okay. Now, we need to try to find a couple of values of x, one of which gives us a negative value, and the other gives us a positive value, so that we know that 0 would have to be in between, right? Now, if you were working this from scratch on your own and you didn't really know what the function looked like, you would probably do what I'm about to do just sort of off on the side, because you might need to play around with several numbers and find some that don't really work until you get the numbers that actually do work. But here, thankfully, the most obvious choices do actually work out for us. So let's see, if f of x equals that, then, so we think about what we can evaluate, right? Well, the simplest number is 0, but we can't take the natural log of 0, so that's no good. We can easily compute the natural log of 1. So let's do that. F of 1 is equal to 3 minus 2 times 1, which is 1, minus the natural log of 1, which is 0, so we get 1. And f of, well, any other integers are going to be difficult to evaluate with the natural log. Let's take something simple that we can do with that and say e. F of e would equal 3 minus 2e minus the natural log of e is 1. 3 minus 1 is 2, so we have 2 minus 2e. Now, if we think about this, e is almost 3. It's definitely bigger than 2. So twice e is much bigger than 4. 2 minus that number is going to be negative. So we found a value of x at which the function is positive, and a value of x at which the function is negative. So that is kind of the computational part of this. Now we're ready to put all the things in place. We go back to the intermediate value theorem and see what the conditions are. F needs to be continuous on the closed interval between these two values, right? Well, so let's think about continuity here. 3 is constant, 2x, I mean, this 3 minus 2x is a polynomial, so this is continuous on all real numbers. The logarithm, the natural logarithm, is continuous on its domain, which is all positive numbers. So as long as we're working with positive numbers, f is continuous. So we can say f is continuous on the closed interval from 1 to e. All right. And f of 1 being 1, actually let me, no, that's fine, yeah. F of 1 is positive, it equals 1. That is greater than 0. And that is greater than f of e. Right, because f of e is negative. F of 1 is positive, f of e is negative, so we have this relationship right here. Therefore, by the intermediate value theorem, there is a number, and we can call this whatever we want. The IVT calls it C, so let's stick with that. There is a number C within this open interval from 1 to e. So a number C that is strictly between 1 and e, such that f of c equals 0. You see, we rewrote the equation to be something equals 0. That something we're calling f. So we're trying to show that there's at least one real number for which f of that number is equal to 0. We found a couple of points of interest, a place where f was positive and a place where f was negative. 0 is in between those, so there must be a value between 1 and e, so that f of c equals 0. Because our function is continuous, this is important. Anytime you use the intermediate value theorem, you have to remark on the continuity of the function. Because if it were discontinuous, you think about imagine you have a positive value here and a negative value there. If a function is discontinuous, then it can just jump right over 0. It might never equal 0, right? But because this function is continuous, whatever it does here and whatever it does there, these ends have to connect at least once, so there has to be at least one point where it crosses 0. There may be more than one, right? This could potentially be a very wiggly function, and it could cross 0 many times. I mean, this function is not. We have some idea of how stable this is, the rough shape of it, hopefully. But in general, we might not know what a function does. So there could be many solutions. But knowing that the function is continuous, the intermediate value theorem guarantees that there has to be at least one value in between where the function takes on any value in between those function values. So that is that constitutes our proof, basically. Not the drawing, that was just illustrating what I was talking about. But this is the basic idea behind the intermediate value theorem. You need to find, unless you're given an interval, if you're given an interval, that's an easier problem. You just evaluate your function at the two endpoints and see what you get. They should be straddling the value that you're looking for. But if not, you may have to kind of experiment a little bit and find those and see what you get. But then, like I said, make sure the function's continuous. Remark on the fact that the number you want is in between the two numbers you got. And then the intermediate value theorem guarantees the existence of a solution in between. Now, part B asks you to use your calculator to find an interval of length 0.01 that contains a solution. We know a solution exists, we just don't know what it is, right? So, you could, with a graphing calculator, you could ask it to just find the 0 of this thing, but that's kind of cheating. And actually, you have to ask yourself the question of how is your graphing calculator even finding that solution? Most of these will ask you for like a lower bound and an upper bound, which when you think about it, that's using, that sounds a lot like what we're doing here, right? We're finding lower and upper bounds on our solution. Most of the routines that calculators and computers use to numerically approximate solutions are algorithms that are fundamentally based on the intermediate value theorem. The idea is that if you tell it that there is a solution between 1 and e, it will evaluate f of 1 and f of e and find at 1 it's positive and at e it's negative, and that tells it that there's a solution somewhere in between. So then what does it do? Well, it chooses a value in between. There are different methods for this. One is called the bisection method, where it picks a value exactly halfway in between. Another one uses linear interpolation, where it imagines a straight line connecting those endpoints and calculates where it would intersect and uses that as its next guess. Each of those have advantages and disadvantages. There are also some more sophisticated methods. If you take applied numerical methods, you'll probably talk about some of those. It's a 400-level course that is taken by a lot of engineering and science majors who want to pick up a math minor. It's very useful. But if we want to do this ourselves with the aid of a calculator, then we probably don't want to get so fancy and have complicated, messy decimals to type in. Let's start just trying simple numbers, right? So let me recopy some of these. So f of 1, this is for part B here. Again, f of 1 equals 1. F of e, the precise value isn't important. The important thing is that it's negative. Okay. So we want to kind of narrow in on a value, narrow in on a range of values that would contain a solution. Now, you don't actually need a graphing calculator for this. As long as you have even a cheap scientific calculator that will compute natural logs, that's all you need. Because we have a natural log in our function. As long as you can evaluate the function, you're fine. So we can look between this. E is almost 3. So let's just see what f of 2 is. Okay, and I don't know why I wrote equals, because I know that won't be an actual integer. You can throw that into your calculator and compute through, and I worked this out. Let me see where I have my notes. F of 2 is approximately negative 1.7. Okay, so let me draw a little picture over here. We have 1. We have e. We know that at 1, the function is positive. At e, the function is negative. And we are trying to figure out where it's 0. So we have just found that at 2, which is, say, around here, at 2 we get a negative number. Okay. Now, there may or may not be a 0 to the right. We don't know. But we definitely know that there's a 0 between 1 and 2, don't we? So we could pick another value, maybe 1.5. Let's take f of 1.5 and see what that works out to. And if we compute that, it looks like we get negative 0.4. Again, it's negative, but you see it's a lot closer to 0 now, right? So we feel like we're kind of homing in on a solution. All right, so somewhere between 1 and 1.5, there's a 0. You could do the bisection like I talked about, or let's try to just keep this to single-digit things, maybe take a 1.2 or 1.3, see what that comes out to. Given that it's 1 here and negative 0.4 here, it probably seems like 1.3 is going to be a little bit closer. So let's try f of 1.3 and see what that gives us. That gives us a positive value of 0.1. Okay, so at 1.3, this is positive. So we know that the 0 is between 1.3 and 1.5. Let's try 1.4. This gives us negative 0.1. Again, these are very approximate. I'm only rounding to one significant figure here because it doesn't matter. These are going to be irrational numbers, but we're just trying to get. All we actually care about is whether it's positive or negative. I'm going ahead and recording the numbers so we can maybe get better guesses. So all right. Well, 0.1 and negative 0.1, it seems like the 0, I mean, we know it's in between those. There's our 1.3, there's our 1.4, the 0 is somewhere in between. These are of approximately equal magnitude. The 0 is probably pretty close to the middle. Let's evaluate at the middle, 1.35. And that works out to be approximately negative 0.0001. That is a whole lot closer to 0. Okay, but it's still negative. So we come back to our last positive value, that was 1.3. We know it's between 1.3 and 1.35. So you might try 1.32 or 1.33, but actually this is really close. So let's go with 1.34. And maybe we'll get lucky. 1.34 turns out to be about positive 0.03. So looking at this, the intermediate value theorem tells us that there must be a 0 between 1.34 and 1.35, right? Because here the function is positive, there the function is negative. It must pass through 0 on its way between those. And the difference between those is 0.01. That is what we were asked to find, an interval of length 0.01 that contains a solution. So that tells us that one such interval, and the simplest one that doesn't require more, any more places than necessary, the interval from 1.34 to 1.35 would be an interval that satisfies this condition. Okay. And if we wanted more precision, of course, we could take this to further decimal places, right? You see how with just a little bit of, kind of paying attention to how close various numbers are, you can keep kind of bisecting these things either in half or somewhat more intelligently, and pretty quickly start narrowing in on the solution you want to as much accuracy as you need. You don't need a graph. You don't even need a graphing calculator, although it is easiest if you have something where you can enter the function and then just repeatedly evaluate it at whatever numbers you pick, right? The easiest way to do this would be to put our function into a y equation, like y1, and then use the table on ask mode to just type in x values and have it spit out y values. That would be the most efficient way to go here. But you don't need that, like I said. As long as you have a way of computing the function, you can just work through this numerically and approximate your solution with much more efficiency than a more random approach. And actually, if you imagine what you would have to do if you did just have a scientific calculator and you had to find the answer through guess and check, this is kind of what you would be doing anyway if you were smart about it, right? You would take a guess, you would take another guess, and based on how close those things were, you would make another guess, and you would keep iterating on this and subdividing. And like I said, that's basically what calculators do anyway when you ask them to find zeros or find intersections between two functions. They basically go through this process. The details are different. They use slightly different algorithms, but it's the same fundamental idea of chopping things off, cutting things down, narrowing in on the solution that you're looking for. Now you can see that this is the 1.35 was a lot closer to 0 than the 1.34. If you want, you can continue to narrow in on this. The actual solution that we're looking for, I'll call this x naught, turns out to be approximately, what do we have here, 1.34996. So you can see why the 1.35 was so close to 0. But yeah, you can play around with that on the calculator and make sure you see how those things work. And this intermediate value theorem is used for a lot of theoretical purposes to prove other theorems and to prove existence of things. And it's also used, as I say, for practical purposes because the idea of it is underlying the numerical algorithms that we use to have computers and calculators solve problems for us anyway.